In today's video, I'm going to talk about the combined gas law. So previously, I've done a video on Boyle's law, which is pressure times volume at starting conditions equals pressure times volume at ending conditions. Temperature is held constant with that law. We've talked about Charles' law in another video, where we have volume divided by temperature at the starting conditions equals volume divided by temperature at the ending conditions. A third video discussed Gay-Lussac's law, which is pressure divided by temperature at starting conditions equals pressure divided by temperature at ending conditions. So if our temperature is constant, we can use Boyle's law. If our pressure is constant, not changing, we can use Charles' law. And if our volume is constant, not changing, we can use Gay-Lussac's law. What if nothing's constant? What if pressure, volume, and temperature are all three changing? We can combine these three laws into one law called the combined gas law. And the combined gas law looks like this. We have starting conditions on the left side of the equal sign, pressure times volume divided by temperature, equals our ending conditions, pressure times volume divided by temperature. Remember, temperature needs to be converted in any of these that have temperature in them. Temperature needs to be converted to Kelvin by adding 273 to your Celsius. You will be given 5 of the 6 variables and asked to find that missing one. So let's look at some example problems of this type. Here's our first example problem. If a 3.5 liter container of gas, doesn't matter what gas, all gases act the same way, at 25 degrees Celsius has a pressure of 1.25 ATM, which stands for atmospheres, what is its volume at STP? So it's asking for the final volume, which is our V2. So that's going to be our X, our unknown that we're solving for. STP stands for standard temperature and pressure. Standard temperature is 273 Kelvin, which is the same as 0 degrees Celsius. But remember, in gas laws, we're going to use Kelvin. And standard pressure is 1 atmosphere of pressure, which is the same as 760 torr, which is the same as 760 millimeters of mercury, which is the same as 101.3 kilopascals. So these are 4 different pressure units that you may see, and these are the standard pressures in those units. Since we were given ATM, atmospheres, we want to use standard pressure in atmospheres, which is 1.0000, however many zeros you want. So that's going to be our final conditions. Remember our combined gas law. We need P1, V1, T1, P2, V2, and T2. Pressure 1, we were given up here in our problem, is 1.25 ATM. The ATM tells you that's a pressure unit. Volume 1, we were given. We were told it was a 3.5 liter container. Volume may also be given to you in milliliters, and that's okay. Just make sure that your beginning and ending volume is in liter. Your beginning and ending pressure is in ATM if that's what you were given. And if you were given milliliters here, then your final volume you'd want to be in milliliters as well. So we don't have to convert either of these as long as our final answers are in the same units. And then we need temperature 1, and temperature 1 was 25 degrees C, but remember we need to add 273 to get it into Kelvin, so our starting temperature is going to be 295, 6, 7, 8 Kelvin. So that's going to be our T1. Our pressure 2, we were told is standard, and we want to be the same units as pressure 1, so standard in ATM is 1 with as many zeros as we want. We'll put 2 since that one has 2 decimal places. Doesn't really matter. And then volume 2, we were asked to find what is its volume, so that's going to be our X, and that is going to come out in liters because our volume 1 is in liters, so when we find our answer it's going to come out in liters. And temperature 2, we were told was standard temperature, and standard temperature in Kelvin is 273. Since we're changing temperature, pressure, and volume, we want to use our combined gas law. So we're going to do pressure 1 times volume 1 divided by temperature 1. Pressure 1 is 1.25 atmospheres. Volume 1 was 3.5 liters, and temperature 1 was 298 Kelvin. On the right side, we're going to have our final conditions, and again, we want to have pressure, the final pressure times the final volume equals the final temperature. So our final pressure is 1 atmosphere. Our final volume, we don't know. That's our X. That's what we're solving for. And our final temperature is 273. So the first thing we probably want to do is cross multiply to get it out of this fraction form. And that means we're going to take the top of this side times the bottom of this side equals the bottom of this side times the top of this side. So it's called cross multiplying because you're going to be multiplying and you're going to cross like this. So this times this times this, diagonal, equals this times this times this, diagonal. That gives us 1.25, I'm going to go ahead and leave out the labels at this point, times 3.5 liters times 273 Kelvin equals this diagonal 298 times 1 times X. So we can go ahead and multiply our numbers together. On the left, we have 1.25 times 3.5 times 273, which is equal to 1194.375. We don't want to cut any digits off or round to any kind of significant digits here in the middle of the problem because that will introduce an error. So we're going to keep the whole number until the very end when we'll round to significant digits. On the right side, we have 298 times 1 times X. So 298 times 1 is just 298X. Now we want to get X by itself. Since this is multiplied, we have to divide by 298 to cancel it on this side, but to keep it equal, whatever we do on the right, we're going to have to do on the left. So we're going to have to divide by 298 on this side as well. So we're going to take our number here and divide by 298, and we get 4.007969, etc. equals X. Now we are solving for volume, and our volume's coming out in liters. And now to figure out how much of this number to keep, we go back to our original problem. This number right here has 2 significant figures. This one, but when we add 273 to it, is going to come out with 3 significant. So you got to remember temperatures are going to be at least 3 because you're adding 273 to them. Then our pressure has 3. And then for STP, we don't really need to factor that in because it's going to be 1.00000. It can have as many significant digits as you need. And our temperature, I used 273. If you needed more, you could use 273.15, which is really the real standard temperature, but often we just round that to 273, but it's actually 273.15 is the actual one if you wanted more precision on that, more sig figs. We don't have to worry about the STP part. So this has 2, this has 3, this has 3. The lowest number is the one that limits how many you keep in your answer. So we go to our answer, we're going to keep the 4 and the 0, and that will give us our 2 significant digits. So our final answer, V2, is equal to 4.0 liters. Let's work another example, and this time you may want to pause it, work it out for yourself, and then hit play to check your answer. Here's our second example that we're going to work on. If a gas sample, again, doesn't matter what kind of gas, they all act the same, has a volume of 295 milliliters at STP, that's standard temperature and pressure, at what temperature will it have a volume of 3.4 liters at 135 kPa? So we are given our beginning conditions is standard, and the units we need, look at your other pressure, it's in kPa, so standard pressure is 101.3 kPa. Our volume is 295 milliliters. Our starting temperature is standard, which is 273 Kelvin. Our final pressure is 135 kPa. And again, this is given to us in kPa, and that's why we chose this one as our standard pressure. If this had been ATM, we would have used 1 ATM. If this had been millimeters of mercury, we would have used 760 millimeters of mercury, those numbers that we talked about in the first problem. Our V2 is 3.4 liters. However, this one is given to us in milliliters. So we need to either change milliliters to liters or liters to milliliters. I'm going to go ahead and change liters to milliliters. It doesn't matter. You just got to get the 2 units the same. You'll get the same answer either way. So we need a conversion factor. 1 liter is the same as 1,000 milliliters. Milli means 1,000. So we're going to have to multiply our 3.4 liters. Liters cancels. 3.4 times 1,000. So that just moves our decimal over 3 places. So 4 is 1 place, 2 places, 3 places. And we now have milliliters. And then our final temperature is what we're being asked for. And it's going to come out in Kelvin because the other one's Kelvin, and we always use Kelvin with gas law problems. If you're asked for Celsius, you would convert it to Celsius at the very end. Now we're going to plug it into our equation. P1V1 over T1 equals P2V2 over T2. So P1 is 101.3 kPa. V1 is 295 milliliters. T1 is 273 Kelvin. P2 is 135 kPa. V2 is 3,400. Our final temperature is what we're being asked to find. So that's how we would set up the problem. Then we're going to cross multiply. So we're going to have 101.3 times 295 times x. Remember, you go down to the bottom. So 101.3 times 295 times x equals 135 times 3400 times our other diagonal, which is 273. It does not matter what order these are in, so you could have said 273 times 135 times 3400 and put the 273 in front. That doesn't matter. We just wanted to get it out of fraction form. So let's go ahead and work out our numbers. On the left, we have 101.3 times 295. So we have 29,883.5 times x. So the x is still there. These two multiply together to give us that. On this side, we're going to multiply all three together. So we're going to have 135 times 3,400 times 273. And that equals 125,307,000. Now to solve for x, we need to divide by this number that's in front of x on both sides. On the left side, that cancels and we're just left with x. On the right side, we need to take this big number and divide it by 29,883.5 equals 4193.18, etc. And remember, this is coming out in Kelvin, our temperature. We go back and look at our problem. We have 3 sig figs here. We have 2 sig figs here. We have 3 here. So we're going to round it to 2. So we're going to keep 4200 Kelvin. That will have 2 significant figures. We had to round that to a 2 because the first one we're changing to a 0 right here is a 9, so we have to round that up. And that would be our answer in Kelvin. If you're asked for Celsius, remember that Kelvin equals Celsius plus 273, which means Celsius is going to equal Kelvin minus 273. So if we want to change this to Celsius, we would take our 4200 and subtract 273, and that gives us 3927 degrees Celsius. Again, if we're only keeping 2 sig figs, we keep the 2 biggest, make the other 0 to keep the distance to the decimal point. So we'd have 3900 degrees C if we're asked for Celsius. And that's how you work a combined gas law problem. You know you're going to need this gas law if you see the temperature, the pressure, and the volume, all 3 changing, and that's when you're going to use it. I hope this has helped, and please subscribe to my channel for other videos.